So today we're going to, I think that we can start smoothly. And today we're going to discuss about automated urban transport services in the framework of the LEVITATE project. In fact, we are going to work on the impact assessment methodologies for automated urban transport services and to see thoroughly these methodologies and the results from their application. It's going to be a tight and intensive program with a short introduction of the LEVITATE project, then the overview of automated urban transport impact assessment, and then we will have specific presentations for the 5 methodologies: microscopic simulation, mesoscopic, automated ride sharing, system dynamics, the Delphi method, and then conclusions and questions and closing. Just to highlight that, first of all, this webinar is recorded, and then that you can use the chat to ask questions or to contribute. And we are going to respond to all chat remarks and questions right after every presentation. Of course, at the end, we will have the possibility to wrap up with additional remarks and questions. But please feel free to ask questions and contribute at any stage, especially during the presentation of the methodologies. So having said so, I don't think that we have something more to add. And I would like to invite Professor Andrew Morris from Loughborough University to make the introduction to the LEVITATE project. Andrew.
So thanks very much, George. Thanks very much, George, and a very good morning to all of you. Welcome to this LEVITATE webinar. My name is Andrew Morris, and it falls on me to give you a brief introduction to the LEVITATE project and what we're intending to do in the project overall, the aims and objectives of what we're trying to achieve, and then I'll hand over to my colleagues working on the LEVITATE project for a more of a deep dive into some of the impact assessment methodologies that we've been using in LEVITATE. And then we respectfully request that you ask questions during the Q&A session that will happen at the end of this particular webinar. So LEVITATE, first of all, stands for Societal Level Impacts of Connected and Automated Vehicles. And the intention is that the project will build tools to help European cities, regions and national governments prepare for a future with increasing levels of automated vehicles in passenger cars, urban transport services, and urban logistics. The project funding is 6.4 million euros provided by the European Commission under Horizon 2020. And the project is led by ourselves at Loughborough University and brings together 12 partners from 10 countries, including renowned research institutes, local authorities, and global partners. It's a 3.5 year project. So we started on the 1st of December and we'll be finishing sometime next year, hopefully in May next year. The project involves 12 partners in total, and the partnership aims to address a combination of technical, stakeholder and implementation challenges involving conducting the necessary research to prepare a policy support tool. The team is also assembled in order to combine all of the necessary competences and expertise in order to carry out the technical evaluations through data analysis and simulations, and to ensure successful dissemination and exploitation of the project results. And then ultimately, we aim to successfully launch the policy support tool to be used by a range of stakeholders, including local and national roads authorities, and policymakers. So hopefully you can see we've got a good blend of research institutions, universities, software and simulation experts, and road authorities in the project. The reason why we're doing the project is overall there are quite high expectations associated with much optimism about what connected and automated transport systems might deliver in terms of safety, mobility, and environmental benefits. But as yet, there's no standard means to predict what's really likely to happen and whether all of the predicted benefits are likely to eventuate, or whether there may be issues associated with the introduction of automated transport systems that we'd not yet realized or anticipated. Also, and maybe less obviously, we need to consider whether the potential benefits that we might predict in one particular metric do not mean that there's a detrimental effect or impact on another metric. So we need to consider all likely benefits and disbenefits collectively. And so this sort of analysis is a little bit more complex than you might imagine, but it's no less important or necessary. So the overall aim of LEVITATE can be described as building tools that will help European cities and other cities for that matter, regions and national governments prepare for a future with what might be predicted to be increasing levels of automation in passenger vehicles and other urban transport services and urban logistics. And then eventually we develop an impact assessment framework, which will be available to policymakers so that they can, they're able to manage the introduction of automated transport systems to maximum effect. And this in turn will lead to technology, will ensure that technology can be harnessed in order to achieve societal objectives. And in order to achieve its objectives, LEVITATE is establishing a number of impact assessment methodologies, which we want to talk about today. And the intention is we'll then establish how these can be applied across a range of possible future scenarios once some automated vehicles become a reality, based on stakeholder inputs, quantification of impact dimensions and indicators, and development of microsimulation models. We're then exploiting these methodologies to examine what might happen within each possible scenario based on modeling and simulation. So, for example, we might want to consider how driverless cars will impact on parking provisions within inner city areas. And we might want to determine what the likely traffic flow into city centres might be if we decide to provide dedicated lanes for driverless cars. And once we've looked at a broad range of use cases and sub-use cases, we intend to bring all of the individual analysis together through establishment of the policy support tool. And essentially, the tool will be available to city authorities and policymakers to assess the impact of a particular scenario, say, for example, congestion, based on the changes that are likely to take place as automation becomes more prevalent. And hopefully, the idea is that this will allow policymakers to study how congestion in inner city areas might change on different roadways if the composition of the vehicle fleet changes as a result of the changes in the uptake of autonomous vehicles. And once the policy support tool has been completed, it will be available for general usage, and the project will thus engage in focused dissemination activities designed to inform stakeholders of the availability of the tool. With that, I'll hand over to my colleagues now who take more of a deep dive into some of the impact assessment methodologies that we intend to use and have been using within the project.
Thank you very much, Andrew. So the framework is set. I think that within this framework, we can get into the specific topic of today, automated urban transport services impact assessment. It's going to be a presentation of the three use cases that we have worked on. It's going to be the presentation of the first of the three use cases we have worked on during LEVITATE project. Use case one about automated urban transport with shuttle services. we are going to demonstrate the results of our work, which followed a three-step approach. First of all, we had to explore the sub-use cases to study and the impacts to quantify, a tenacious work which took quite some time in order to fit what we want with what we can. A workshop with stakeholders. And after setting the sub-use cases and the impacts with several trials, we have proceeded to the quantification with the main methodologies, the traffic microscopic simulation with AIMSANG, the traffic mesoscopic simulation with MATSIM, system dynamics models, and a Delphi study to complement the above three methodologies. And today we are happy to say that we can deliver a full set of results and a nice combination of results from the different methodologies in a synthesis that we are going to see in a while, including policy recommendations. In fact, the automated urban transport sub-use cases concerned point-to-point automated urban shuttle service traveling between fixed stations and complementing existing urban transport. That was either point-to-point shuttle services connecting two modes of transport or implemented in a large scale network. And secondly, we were working on autonomous mobility on demand with Flexim on-demand automated shuttle bus service, including anywhere to anywhere, last mile, and e-hailing, which all three complement existing urban transport. In fact, in this table, you can see all the impacts. We're going to have to dig more into the detail in the coming presentations, the impacts, the methodologies, and the results, covering from traffic and travel indicators to safety and environment and energy efficiency, leading to a comprehensive approach. So, having said so, I would like to start already working on presenting the results, and perhaps we can move on to the microscopic simulation methodology presented by Maria Economou from NTUA, which is going to present the methodology and the results of its application. Maria.
Thank you very much. Hi everyone, my name is Maria Economou and I am a researcher at the National Technical University of Athens. This presentation is about macroscopic simulation on automated urban transport. First of all, the macroscopic simulation method was selected in order to examine the impacts of connected and autonomous vehicles, as well as autonomous transit services, mainly on traffic, road safety, and energy efficiency. For that purpose, three different sub-use cases concerning different automated urban public transit services were implemented in the Athens network using the AIMSANG mobility software. First sub-use case concerned a point-to-point automated shuttle service connected to modes in a small-scale network. The second one was again a point-to-point automated shuttle service connected several points in a large-scale network. The last one was a non-demand mobility automated shuttle service operating in a large-scale network. These sub-use cases were complemented to the existing public transport. The first network on the right side is the small-scale network and was used for the first sub-use case, the point-to-point automated shuttle service, and approximately included 60 centroids, consisted of approximately 150 nodes and 350 road segments. The second network was the large-scale network and was used for the second and third sub-use case, included approximately 300 centroids and consisted of 1,000 nodes and 2,500 road segments. Regarding the simulated scenarios, for the first sub-use case, a baseline scenario was simulated, which was the no transit service operation scenario. Also, mixed traffic conditions during peak hour was tested as well as the existence of a dedicated lane for the service during peak hour again. Also, mixed traffic conditions during peak hour while an incident occurred on the shuttle bus route was simulated for this sub-use case. Regarding the off-peak hour conditions, mixed traffic conditions, as well as the existence of a dedicated lane for the shuttle bus service, were also investigated. Regarding the second sub-use case, the point-to-point shuttle service in a large-scale network, a baseline again was simulated, as well as mixed traffic conditions during both peak and off-peak hour, and the existence of a dedicated lane during peak hour. The last sub-use case, the on-demand shuttle service, included a baseline scenario, two scenarios that 5% of the demand was served by 50 shuttle buses of 8 and 15 passenger capacity respectively, and the last two scenarios was for 10% of the demand to be served by 100 shuttle buses of 8 and 15 passenger capacity each. Some additional microsimulation specifications were that two main driving profiles were simulated for modeling connected and autonomous vehicles. The first one is the first generation, that is a cautious driving profile. The second is the second generation, that is a aggressive driving profile. Also, the autonomous shuttle buses for the three services were first generation of connected and autonomous vehicles. And regarding the implementation of them, different market penetration rate scenarios were simulated and are presented in the table on the right side. These scenarios are 8, and the market penetration rate is increased by 20%. The first one included 100% human-driven vehicles, and the last one 100% of second generation of connected autonomous vehicles. Also, the second generation was introduced when the first generation reached the 40%. Regarding the macroscopic simulation results, for each impact, a graph was extracted for each simulated scenario for both peak and off-peak hour. Here we have the traffic-related impacts and environmental impacts. And according to these graphs, we can see that the existence of the shuttle bus service led to increased delays and total distance traveled. Also, the existence of the dedicated lane for the shuttle bus service increased delays and decreased travel distances during peak hour, while during off-peak hour remained the same. Traffic emissions were found to be significantly lower when the market penetration rates were higher. Regarding the safety impact, crash rates were extracted and the corresponding graph. This graph shows that the crash rates presented many oscillations due to the smaller size of the network. Also, automation among the entire fleet, as well as the addition of the service, reduced the crash rates at high penetration rates. And finally, for the intermediate states, we have mixed results and increased crash rates for the scenario in which the second generation of connected and autonomous vehicles was introduced. Regarding the second sub-use case, which is the point-to-point shuttle service operating in a large-scale network, the same graphs were extracted and illustrated that automation decreased delay time and increased travel distances during both peak and off-peak hour for the last two market penetration rate scenarios. Again, traffic emissions were significantly lower for all scenarios, while the different implementations of the service did not present any significant differences. The corresponding crash rate graph showed that none of the scenarios predicted an increase in crash rates, even at low market penetration rate scenarios. Compared to the baseline, both peak hour scenarios showed the same trend in crash rates. And for the off-peak hour scenario that showed the fewer driven kilometers, the crash rate was higher at all market penetration rates. Regarding the last sub-use case, the on-demand shuttle bus service, the implementation of the service led to decreased delay times and did not show any significant differences in total distance traveled, and traffic emissions were again significantly lower when the market penetration rates were high, and the different implementation types of the service did not present any significant differences. Crash rates showed that were reduced for all market penetration rates, and the addition of the service resulted higher predicted crash rates than the baseline scenario. To conclude, the point-to-point automated shuttle bus service led to increased delays and total distance traveled, while on the contrary, the on-demand shuttle service decreased the delays and showed constant driven kilometers. In addition, the introduction of the different shuttle bus services did not show significant differences in crashes as well as in emissions, which were significantly lower when the connected autonomous vehicles, the number of connected autonomous vehicles was increased. Finally, in a small-scale network, the automation did not affect traffic-related measurements, while in a large-scale network, decreased delays, increased distance traveled, and reduced crashes were revealed. Thank you very much.
Thank you very much, Maria. It was very comprehensive with methodology presentation and results. Perhaps now we could proceed to the next presentation concerning mesoscopic simulation. And I would like to invite Johannes Müller from AIT in Vienna to make the presentation.
Okay, hello everyone. Just minimize the screen. Perfect. I hope you can see the screen now. My name is Johannes Müller. I'm with AIT, Austrian Institute of Technology. We are based in Vienna, and also the mesoscopic simulation that I showed to you is done in Vienna, not in Athens. We have done the one sub-use case of on-demand automated urban shuttle services, and we have there two scenarios. One is the anywhere to anywhere shuttle service, and the other one the last mile, as it was already introduced by George in the beginning. Let me introduce to you the two scenarios that I will present to you. One is the anywhere to anywhere service. So you can imagine it's not like in the point-to-point service where you do have strict routes and the bus just goes on these routes and have just some bus stops, but instead you have an area, in this case, the orange and the red area in the inner city and the city center, that's how we called it, where the service is available. And it can be booked like a Uber service, like a taxi service. And it can basically, you can hop on and hop off at any link in this network in the dedicated area. We have worked with two different fleet sizes. Seems to be a bit small, but regarding the size of the simulated population, which is 12.5%, it actually compares to the current taxi fleet size, which is operating in the whole area of Vienna. The other scenario is a bit different. So we do not focus on the inner city area, but instead go to the suburbs, where there's actually, it's quite uncommon compared to current car sharing services, and where the operators usually focus on the very dense inner city areas. We also thought that it might be interesting to analyze what happens if we really enforce people using the service in the suburbs. And this is why we called it the last mile shuttle. You see here the map where we have restricted the service. And we have not only restricted it to these 16 zones, it's also that you cannot do any trip from one zone to another one. So you cannot do any cross-city trips, but instead you have to stay within your zone. So you cannot start your trip here and then just go to another trip in another zone. By this, we ensure that the vehicles are used very wisely, so they are not just used for a simple supplement for the urban transport. Really, we can restrict it and enforce the more intermodal use with public transport, especially. All these zones have usually a very good public transport hub. So there's an underground station or suburban train station, which operates at least every 10 minutes, let's say. In a rush, in peak hours, it's usually more. For all these zones, we have a different fleet size, which is dependent on the number of facilities. Facilities are places where an agent in the simulation can do an activity. So here we work with a fleet size of 12 or 25 vehicles per 1,000 facilities, resulting in more than 1,000 or more than 2,000 vehicles. What are the general configurations in the simulation? First, a very important parameter is the value of travel time saving, or also the marginal utility of travel time, which needs to be configured. Here we assume, according to literature, that the VTDS of this shuttle services is around 75% of the VTDS of a car. We also work with different market penetration rates, as Maria has presented, and here we change randomly some of the agent's private car to an autonomous car or to this connected automated vehicle. And we work also with two generations. So the first generation has then 80% of the VTTS, and the second generation, like the automated urban shuttle services, the 75% of the VTTS of a car. We work with slightly different capacities of vehicles. Only 4 persons have a space in such a vehicle. That's because otherwise the simulation is assumed to not work properly, because you need to pick up really every person on a way, and to have a shuttle bus which randomly picks up all the people will lead to very high detours, and it is not supposed to be reasonable to have these high detours, and this is why we restrict it to a kind of normal car service. All vehicles are distributed initially randomly, and we also work with different marginal utilities of monies representing different economic status. You will see the results. Nonetheless, I will not go further deeper into that because of the time constraint in this presentation. One parameter that we also changed for the different market penetration rates is the flow capacity factor. So we assumed that the flow in the simulation improves with a higher market penetration rate. And you see, we don't make a difference between first and second generation CAVs in this case, but just keep it then constant once the 100% is reached. This refers to the private vehicles. The presented impacts will be, in this case, only 3. So I will focus on the travel time, the amount of travel, and the model split. We also could deliver the vehicle utilization rate for the OSS and for sure also emissions, but in this case we referred to the micro simulation. So you will see in the next slides the travel time, amount of travel, and model split. Let's start with the travel time. Here you see the different baselines. As I said, I will only focus on the normal line and not on the dashed and dotted lines, where we see a decrease of travel time once we have more with a higher market penetration rate. The reason for that is that we have more trips done by car with a higher market penetration rate because of the traffic flow. When we introduce the anywhere to anywhere service, we see that the scale, so this is the percentage relative to the baseline, so the figure that I just showed before. And we see that it improves the travel time, and the more vehicles you have, the more it is reduced. Interesting is this point here, when you introduce the first CAVs into the fleet, that is assumed to come from the fact that this flow capacity factor, which is linearly increasing, has nonetheless a non-linear impact on the simulation. So it is really a difference if you have these vehicles in even just a small share in the beginning than if you don't have any of these. For the last mile, you see first an increase actually, but then it's kind of a smaller increase, which also goes close to 0. So you don't have rather any effect for a high market penetration rate, but a slight increase if you just have conventional cars. The amount of travel refers to the average kilometers traveled over a year. So this is also why you see here the kilometers traveled for every agent. And you see a similar effect then for the travel time, that it's decreasing with a higher market penetration rate. And let's see what happens if we have the different scenarios. Here we actually see an increase the more vehicles we have, which is also not surprising, because if you have more vehicles, people will use it more, meaning also they will subsidize their car trips, which are usually a bit more straightforward, and by this shuttle services, which might also include some detours. For the last mile scenario, we have a lot of wiggling in the graph, meaning that we have a smaller increase of the amount of travel. But yeah, the effect is really marginal in our opinion. Let's move to the model splits. So here the graphic visualization is a bit different. We do not have the baseline, or the baseline is better said, presented here with these black boxes. So this is also to give you a reference to what the actual baseline is like. You see that if you just look to this graph, that the increase, the car travel, the private car use increases with a higher market penetration rate. Then you see here the difference in the scenarios with the different fleet sizes here for the 220 vehicle fleet in comparison to the baseline. And you see that the private car model split reduces, as well as the public transport. The public transport is in our case now considered separately from the automated urban shuttle services. So they build this additional gray part of the histograms. Interesting is that the active modes increase with a higher market penetration rate of CAVs. And you also see the effect if you increase the fleet, then you have even a stronger effect of cannibalization. And it's not cannibalizing from the active modes, but rather from the car modes. And this was now here for the anywhere to anywhere shuttle services. If we do it for the last mile, we see that the cannibalization from the car modes is actually stronger than in the anywhere to anywhere service. And the difference between the fleet sizes in the last mile scenarios is just marginally. Let me summarize. So the impacts that we analyzed and I presented: travel time, we have shorter travel time with a higher market penetration rate. The last mile automated shuttle service leads to a marginal increase of travel time, and the higher the OSS fleet size reduces the travel time even more. For the amount of travel, meaning the vehicle kilometers traveled for each agent, it decreases if the market penetration rate of CAVs increases. And we see that higher fleet size leads to a higher amount of travel. For the model splits, it's actually interesting to see that a lot of cannibalization comes from the car and public transport. And we see that, especially in the last mile scenario, the intermodal use seems to be well used. So people change their mode, so they can change at the public transport hub in these zones and replace car trips more than they would replace a whole public transport trips. Okay, that's it from my side. Thank you very much, and I hand back to George.
Thank you very much, Johannes. That was very interesting, and especially seeing how we go from methodology to results. And results which have never been available so far for automated shuttle services. We might now move to the next methodology, which concerns automated ride sharing. It's going to be presented by Mrs. Raya Hawari from Loughborough University. So Raya, the floor is yours.
Okay, thank you. Okay. So hello everyone. My name is Raja Hawari, and I am a research associate working on LEVITATE project and within Loughborough University. So today I'm going to present a sub-use case under the passenger transport use case, which is related to automated ride sharing. Automated ride sharing. So so in general, on-demand mobility services such as car sharing, ride hailing, and 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 ride-hailing and ride-hailing have gained increased popularity during the past few years, and they have become an increased common travel solution, especially in urban area. So in fact, on-demand mobility services can positively impact transportation, land use, the environment, and society. And combining them with the emerging technology of autonomously driving vehicles could 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 amplify those benefits. So the aim of this sub-use case is to investigate the the impact of introducing automated ride-sharing services on the efficiency of transportation system, and also to investigate the impact of user preference to use the service as for individual trips or for shared trips on the on 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 the performance of this service as well. So within this sub-use case, we propose an automated ride-sharing service for based on a door-to-door service, like offered by shared autonomous vehicles fleet, and it proposed two sharing option for the users. First, solo trips, where the users can use this those apps for individual trips, or shared SAP, or as shared rides, where users can share their ride with strangers. So in order to determine actually those two options are the choice between those two options are based on the passengers' willingness or preference to share their ride with others. So for this, we define four scenarios based on this willingness to share, going from 20%, with only 20% are willing to share their ride, and 80% will use this service as a car sharing or a taxi service. This means for individual trips, and until 100% will all passengers that will use this service are willing to share their trips. So for the implementation of this sub-use case, we used a calibrated and validated microsimulation model of a suburban area from the Great Manchester region, and with mixed vehicle fleets under evening peak hours. So for the assignment of or matching like trip request with vehicles with shared autonomous vehicle, we model this problem as a vehicle routing problem with pickup and delivery with time windows. So unfortunately, due to the time allocated for the session, only the micro simulation result will be presented during this presentation. Okay, so in terms of scenarios, we defined scenario first, the baseline scenario or no policy intervention, which is based only on the current situation with increasing penetration rate at going from 0 to 100% with 20% increase. So, and concerning the automated ride-sharing scenarios, we defined them based on the following characteristic. First, the demand. So here we defined we use three types of three shares of demand, going from 5, 10, and 20% that are going to be served by this service, and they are initially from the private vehicle demand. Then in terms of willingness to share, as I already mentioned, we are using like 4 percentages from 20, 15, 80, and 100%. Concerning vehicle capacity, since this sub-use case is is used for passenger transport, we use only the capacity or sorry of the ordinary capacity of a four-seat passengers. Then concerning driving profile, we have to the fleet of shared of the shared vehicles will be will contain two types of profile: first generation cabs and second generation cab. Okay, this already been explained by my colleague Maria concerning the first generation, second generation, the difference between them, and concerning difference between them in terms of sensing, in terms of of decision making and other criteria. In terms of scenarios, this in terms of automated market penetration rate, we have 8 market penetration rate, as I already mentioned, going from 0 to 100 with different 0 to 100 with 20% increase. Okay, so to model this to model this sub-use case, we proposed we took into consideration the following assumptions, where all cab are all personal and shared are considered as electric vehicles, and also that we suppose that the battery capacity are supported for whole day operation for each staff. That's mean that the charging station are not included included within this sub-use case. We also we also assume that the parking spaces are enough for all for the shared vehicle in all stations, as well as in concerning pickup and drop-off locations, since we have another case sub-use case sub-use case that investigates its impact. We are not going to address it in this sub-use case. Concerning the preference of ride sharing or the willingness to share, we only use a parameter of with two status: is the passenger is willing or not willing to use this sub-use case. And of course, there no cancellation for are allowed, and the request for and also request trip request is referred to only one traveler. So in terms of results, so we have those plots refer to the impact on the delay. So concern as you see, like on general, we can see that we have an increase on traffic delay, an increase on traffic delay, and that's mean that we have more congestion, and this could be and this and this could be caused by first the length of the trips, the length of the trips, as well as the empty distance traveled, and also with the behaviors of or the way those shared vehicles circulate the network. For example, they can use some secondary or minor road, causing by that more congestion. So, and in terms of travel distance, we can see that we have a wiggly shape. Actually, this is the wiggly shape. So we can start first with the baseline, which is the darker, which is represented by the darker line, or darker line in the plots. So as you can see, so we can see that the results are kind of inconsistent with the market penetration rate, and this could be related to the interaction between the different vehicle types. That means first generation, second generation, and human driven vehicles as well, which could also cause more which could also cause more congestion. And so in terms of environmental impact, on general, since we already suppose that those vehicles are electric vehicles, so we can see that we have a constant decrease. We have a decrease of CO2 emissions. But in terms of automated ride-sharing service, when we compare to the baseline, we can see that it has that it has a negative impact on emissions. I mean, for example, we can see that we have taken the 20% demand with 100% willingness to share, we can see that we have a maximum values of 5%, same for 10% demand and 5% demand. So, and this is also due to the congestion. So in term of safety impacts, actually for within Levitate, we use the crashes as a KPI to assess the impact of the impact of gas, the impact of gas. So in order those crashes are estimated based on through micro simulation and surrogate safety assessment, and that are used to get the conflict. Then we translate those conflict into crashes using the probabilistic method proposed by Professor Andrew Tarko. So those are and the following plots are the results for the are the safety results regarding automated ride sharing interventions. So as you can see, in general, that we can see that the safety is improved with increasing market penetration rate. But in terms of automated ride sharing scenarios, we can see that they are creating more risk compared to the baseline, and this is also is related to the congestion and the way those shared vehicles are circulating the networks. Okay, so to finalize this presentation at the end, what the key findings of this sub-use case, so that is we can see that the introduction of automated ride sharing has a negative impact on the traffic performance, and or actually it can worsen traffic situation in terms of delay compared to the baseline, and this is due to first the length of the trips, empty distance traveled, the way those SAVs, as already mentioned, circulate in those networks, and also this congestion has direct impact on emissions as well as safety. So, but from the results, we can see that with higher market penetration rate and higher willingness to share, we can potentially mitigate those adverse impacts. For example, in terms of in terms of delay, we can see that with a full market penetration rate under 100% willingness to share, we can have we can have a performance similar to the almost similar to the baseline scenario. So but what we can learn from this sub-use case is that on-demand mobility is not always the answer to solve the congestion problem. Sometimes based, of course, based on the characteristic of the network or the population as well, could cause more congestion. So for this, more policies, the right policies need to be put in place in order to prevent or to prevent those adverse impacts. So I think that's it. Thank you for your attention. So I'll go back to you, George. Thank you.
Thank you very much, Raja. It's, a lot of results. We have to digest them, but all the presentations will be available and we can further dig in all these results. Now we might move to the next presentation. It's the time of the famous system dynamics methodology. And I would like to invite Martin Zach from AIT to make the presentation on system dynamics. Martin.
So I was still muted, sorry. I hope you can hear me now. Okay, well, system dynamics, I did this work together with Anna from Loughborough University and Fritz Bielefeld from SWAF. So just a moment, yeah, it works. One of the strong points in the LEVITATE projects is really the multi-method approach that we have used to investigate a large variety of impacts for a variety of sub-use cases. So system dynamics was used more or less just to supplement these other methods, which we have also been heard of today. In particular for some of the impacts which are not so easy to estimate via micro simulation or mesoscopic simulation. So if you really take a systems perspective and look at these dependencies in a system dynamics model, there are some particular strengths also of system dynamics, like when you want to investigate the cross dependencies between different domains, like transport and population or public space usage and so on, land use. It's also particularly suitable when you want to study the behavior over a long time range. So also looking at the long-term effects. And also system dynamics is suitable especially to experiment with various changes of the system in terms of policy interventions. So when I'm really changing one of these input parameters, how would the impact variables change in a relative way compared to the baseline? And here we considered that system dynamics can provide some useful insights. Last point here to mention is that the results, both of the mesoscopic simulations and also the microscopic simulations, have been partially used as inputs to the system dynamics model. So for example, our model here, which I showed today, is based, or the data are based also on Vienna and closely aligned with the mesoscopic model that has been presented by Johannes and was done also together with Gerald, another colleague of us. But for example, if we speak about time delays for certain sub-use cases, like Raja has explained in the previous talk on the automated ride sharing, that there are some delays in some cases. So this is typically also a result that would can be considered as an input to a system dynamics model to predict some further indirect impacts. So in this 10-minute time slots today, I will just give you a very quick insight into the basic model and show you a few example results for the sub-use cases which are handled in this webinar today. Well, to give you an overview of the system dynamics model, it's maybe the best to show this in form of a simplified causal loop diagram, which shows the structure. So the three bold boxes which you see in the upper part of this picture are defining the basic structure. In system dynamics, these are called stack or level variables, which on the one hand is the population, So we have a population model based on abstract zones. So that's the disaggregation on the geographic level. And we are segmenting the population into age and income groups. In the center and at the very heart of this model, we have the travel demand and the number of trips, which also are based on considering the zones as origin and destination matrix. And of course, we look at the modes, where we have public transport, active modes, and individual car use. And finally, the third box here is the use of public space, like using it for driving lanes, parking space, multifunctional areas, whatever. There are three red variables here, which are typical outputs, which are calculated by the system dynamics model. So we have looked at the model splits. We have calculated demand for parking space and the average commuting distances. The demand and the trips are more or less influenced by generalized costs, which are composed or depending on these three other variables you see here in the model. And just to give you a few more details on this, how does the automation and the automated vehicles come into the model here? It's simply by assuming certain dependencies here of these four variables. How does the automation influence, for example, the travel time? What about the sub-use cases? So today I'm just touching these two. The first is the automated urban shuttle service. More concretely, we have, we'll just show you here results of the last mile shuttle service, which in this simplified model, it's just influencing the attractiveness and the travel time of people who are using it. The second one, which is where Raja presented the microscopic simulation results, automated ride sharing, which is a little bit similar also to what Johannes showed on these on-demand shuttles, which are not really restricted, so you can take it for almost any trip, and it also has some impact on the travel costs and travel time. One important behavior also of system dynamic models would be the existence of so-called feedback loops, which typically leads to some balancing behavior. Of course, also in the traffic model itself, it's clear when you have, let's say, more people going by car, then this causes congestion. So this would have an impact on the travel time, and then it would also stabilize itself. But in addition, we have also some more, let's say, complex feedback loops. For example, a dependency between the number of trips and the use of public space, which is involving really a lot of different variables. Another example for a quite long-term feedback loop is then when you have changes here in the generalized costs that might lead to a relocation of people. For example, also due to automation, that people decide to move out of the city to outer zones. And it's still better for them, at least in this simplified model, because of the lower generalized costs and maybe the use of travel time for other purposes also and for working. So back to the overview, I just will show you now 2 or 3 slides with results for these red variables and for the sub-use cases which I have been mentioning. Let's start with the model split here. So this is what you see here is the model split for public transport. The bold black line here is the baseline, which means, and this is, I think, in good consistency also with the mesoscopic results, that if you just do not consider any additional sub-use case, but you just look at this model split as a function of the AV market penetration rate, you see that with increasing automation, the use of public transport is decreasing. On the other hand, and now it's important to say here, also I think Johannes mentioned a bit on that, in this model, yeah, we assume that the use of last mile shuttles, which you have here, the last mile shuttle would be part of the public transport. So this means it really will increase the mode share for public transport. And the same is true also for the automated ride sharing. And here you see really that with these measures, and of course certain underlying assumptions, you manage to increase the model split for public transport. We have a slightly different behavior for the active modes. First of all, we see here that there's a decrease in the baseline already, a quite significant decrease due to automation. And the automated ride sharing is more or less even amplifying this effect or make it stronger, and even more the last mile shuttles. I will skip now one further result I have on the demand for parking space, simply because there is no significant impact of these two sub-use cases. So we have other policy interventions like road use pricing or parking pricing, which would have significant impact, but not the last mile shuttles or automated ride sharing. So the last plot I'm showing you today is the impact, and it's a quite long-term impact on the commuting distance. So the black bold line, the baseline, shows that this is some relative commuting distance. So I'm really trying to forget about all the other effects. I'm just looking in this simple model, yeah, what's the impact of automation? And I mean, not unexpectedly, there with increasing automation, there is a slight increase in the commuting distance in this model. But even more interesting maybe is the impact now of certain policy interventions or sub-use cases. So the last mile shuttle, which we also have to say here, if you might remember now the map of Vienna that Johannes was showing. So this is quite similar here, that in the outer zone of the city, but it's still within the city itself, we are introducing last mile shuttles, but we do not have last mile shuttles in the vicinity of Vienna, so outside of Vienna. And so this means this concept really would prevent that people are moving out of the city. On the other hand, automated ride sharing would increase this commuting distance compared to the baseline. So this was just really a few example results for these sub-use cases. Okay, that's I do not have any written conclusions here, but let me just finalize this presentation with saying that, well, with the system dynamics results, we tried to also check the consistency across sub-use cases, across methods, and where we have some deviations, it's always good to analyze these and see, well, what are the special assumptions? Yeah, what are the reasons here? And on the other hand, I think we can use, and we have used the system dynamics model to extend and extrapolate this multi-method approach for further impacts that cannot be done with other methods. And we can have a better variation of certain policy interventions. Okay, that's all from my side. Thanks.
Thank you very much, Martin, for a very comprehensive presentation of the methodology and the results. Of course, several conclusions can be drawn if we further dig into the data. We may now proceed to the last methodology. It is the Delphi method to be presented by Giulia Russo from NTUA to give us your results. Giulia.
Yeah, hello everyone. I'm Julia Rousseau and I work as a researcher on the LEVITATE project in National Technical University of Athens, and I will now present you the qualitative impact assessment method used in LEVITATE, which is the Delphi method. I will start by a brief description of the background of the method and how this was used within the LEVITATE. And then I will present the impacts and the results only for the impacts that were quantified by this method only, and finally some conclusions. So the Delphi method is a process used to arrive at a collective and aggregate group opinion or decision by surveying a panel of experts. The Delphi methodology is based on a repetitive interview process in which the respondent can review his or her initial answers and thus change the overall information on each topic. This presupposes, of course, that the participants will be willing not only to give some answers on the topics, but also to repeat the interview sometimes more than 2 cycles. The Delphi method presents several positive characteristics and features, such as the anonymity of experts, which assures free expression of opinions provided by the experts, and we avoid social pressure, and experts can change their opinions or judgment without fear of being exposed to public criticism. Finally, this method provides control feedback, as experts are informed about the views of the other experts who participated in the study. So within the LEVITATE, the Delphi method was used to determine all impacts that cannot be defined by the other quantitative method that we presented earlier. Initially, a long list of experts was identified for each use case, and we contacted them asking to express a willingness to participate. Those who responded positively participated in the main Delphi process, amounting to 70 experts in total. The Delphi method consisted of 2 rounds of emails. During the first round, experts received a questionnaire regarding 2 to 4 automation interventions related to automated urban transport, passenger cars, or automated freight transport. And they were divided in 7 groups, each group with a different questionnaire related to a specific type of interventions based on the expert's area of expertise. They were then asked to evaluate the potential influence of the proposed interventions on different impact areas. And then their answers were analyzed in order to create anonymous summary data for the different interventions. These first round results were then distributed with the second round questionnaire and gave the respondents the opportunity to reflect on the first round outcomes before providing their answers again, which led sometimes to respondents changing their first round answers to something conforming more to the answers provided by the other respondents. The automated urban transport questionnaire included 5 scenarios. The baseline scenario where no intervention is applied apart from the introduction of automated vehicles in the urban environment. Then we have the point-to-point automated urban shuttle service, the anywhere-to-anywhere, the last mile automated urban shuttle service, and finally e-hailing. So after the reception of the first Delphi round questionnaires, we had some aggregation and coding and analysis in order to create the summary. And then in order to identify the influence of the scenarios on a specific impact area, the percentage equal with the average of all the first and second round answers was extracted. Now I'm going to present you the results for the 5 impacts that were identified only using the Delphi method, starting by vehicle operating costs, which is considered as the direct outlays for operating a vehicle per kilometer of travel. And according to experts, the baseline scenario will lead to a slight increase for AV's market penetration rate up to 40%, and then to a small reduction of vehicle operating costs for AV market penetration rate up to 100%. And then, as you can see, the point-to-point and anywhere-to-anywhere automated urban shuttle services both reduce the most vehicle operating costs and are suggested to be the most efficient services, which is explained by the fact that they both merge the positives of automation and ride sharing in public transport. In the second round of the Delphi, participants stated that they agree with the first round results, and some of them suggested that maybe the baseline scenario will have a higher reduction in the long term for vehicle operating cost. Then the access to travel is defined as the opportunity of taking a trip whenever and wherever wanted. And the general expert's opinion was that the introduction of automation in the urban transport will increase access to travel. And as you can see, anywhere to anywhere and point-to-point automated urban shuttle services, again, seem to be the most efficient scenarios for this impact. In the second round, again, experts agreed with the first round results, and were some suggestions that maybe these scenarios will not very much affect this impact. Then for energy efficiency, we have already seen from Maria that emissions will reduce with the introduction of automated vehicles and automated urban shuttle services in the urban environment. And as we can see here, energy efficiency also increases with the introduction of these scenarios. And we can see that point-to-point and anywhere-to-anywhere are the automated urban shuttle services are the scenarios that improve energy efficiency the most among the other urban transport scenarios. In the second round, experts agreed with the first round results, but there were suggestions that the anywhere-to-anywhere automated urban shuttle service and e-hailing will in fact reduce energy efficiency because they will use the roads throughout the entire day. Of course, their suggestions were taken into consideration for the final calculations that will be integrated in the policy support tool. And then we have the public health, which is defined as a subjective user's rating of public health state related to transport, such as air quality and noise pollution. And the general expert's opinion in the first round was that all automated urban transport sub-use cases, including the baseline scenario, will lead to a small improvement on public health, and which is also compatible with the microsimulation results for reduced emissions. And as you can see, point-to-point automated urban shuttle service is the most efficient scenario. In the second round, experts agreed with the first round results, but suggested maybe that automation could have a negative impact on public health, as they considered that people will tend to use more automated vehicles than the active modes of travel, such as walking and cycling. Finally, the last impact that was calculated using the Delphi method was accessibility in transport, which is the degree to which transport services are used by socially disadvantaged and vulnerable groups. including people with disabilities. So as we can see, the baseline scenario is the most efficient one and has the biggest impact, positive impact on accessibility in transport. And in general, experts agree with these trends. So some conclusions regarding the impacts that were quantified using the other methods presented before. The results were also compatible with these methods, and the Delphi findings were also compatible with the outcomes of the literature review, which means that in general these trends show a little bit the expected future after the introduction of these studied automated urban transport services. Some limitations that are posed by this method are the number of the experts, the specificity of the scenarios, and the accuracy of their estimations. But the Delphi results will be used to fill in the policy support tool when no other method can. And this approach can be updated when cooperative and connected and automated mobility reaches increased maturity, and we can revisit these results for future efforts in other projects such as LEVITATE or in broader research. So thank you very much, and we're going back to Professor Yannis.
Thank you very much, Julia. It was the last methodology, but the most qualitative with very nice results. Perhaps now we can move on smoothly to the questions and the discussion. There are already some very nice questions at the Q&A. So perhaps we can start already with Maria responding to the first question from Mohit.
Thank you for the question. Crash rates were higher during off-peak hour. Indeed, probably due to the increased speed values, as the number of vehicles was lower, approximately 40% lower for these scenarios, vehicles were able to drive in higher speed, and that probably caused the higher crash rates for these simulated scenarios.
Thank you very much, Maria. And then there are two nice questions to Raya. Could you please, Raya, provide some insight?
Yeah, sure. So concerning the first question, which is, I said, can you please explain on the reason why automated ride-sharing services can increase traffic congestion? So for the reason for this congestion is, I said, it's basically we have two actually. First is the interaction between vehicles, between different type of vehicle, first generation, second generation, and the human driven. So due to those difference on reaction time and gaps, this creates some kind of congestion. Second, it's due to the way the shared vehicle circulate the network. By this I mean based on the matching or on the optimized road for the shared vehicle fleet. Some roads can contain some infrastructure that are not prepared, for example, for like high traffic. So that, for example, secondary or minor roads. So that's why it could create like extra some extra congestion in those area. So I hope I did answer the question. So for the second question, they said, is there any is there information about the proportion of kilometers traveled by empty vehicle compared to the trips moving people, and how can this empty traffic can be minimized? So yes, there is information, but of course not for microsimulation. It's from the optimization process, because we measure the request and optimize the routes before then give them as an input for the microsimulation. So we have that results, but unfortunately, since we don't have enough time, we didn't present them in here. And in terms of how those empty trips can be minimized, this could be minimized if we encourage people to share to use the service as a shared service instead of car sharing or car sharing or taxi service. That's mean for individual trips. So
Thank you very much, Raya. And we have two more questions about to Martin.
Yes, okay. Let me, I think the first question was on use of public space. Okay, I do not see my, sorry, just, okay, I will just quickly release my desktop. I thought maybe it's best to show you that part of the model. The question was explain a little bit more in detail how the public space is considered in the system dynamics model. So at the bottom of this diagram, you see, let's say, three purposes of public space. So in this simplified model is let's say we consider a certain part of public space, yeah, where you, of course, you can feed this with data, yeah, which of the public space is used either for parking or for driving lanes or for other multifunctional areas. And well, you have a certain value at present, and then what might not be readable perfectly, you could think of policy interventions, which are in yellow here, to have a conversion, yeah, between these. For example, two of the sub-use cases was conversion of public parking space, yeah, which might not be needed anymore in this quantity, into public space for walking or cycling, yeah, multifunctional areas, cycling lanes.
Yeah, sorry, we are at 11:30. If the system goes down already, just to say thank you. If the system doesn't go down at 11:30, we continue. Please, Martin.
Okay, so I hope that that gives a little bit insight into this and how it was modeled. Yeah, but let me stress here, it's really a very simplified model. Yeah, it's not a very sophisticated model, and that maybe is also the good transition to the second question, which was about public health. Well, this was considered when Hitesh, our colleague from Loughborough University, brought system dynamics into the play, but it turned out to be a little bit ambitious. Why? Of course, we could include it in a very simple level, public health, and see what are the influencing factors, but then maybe the results would not be very much different from what we anyway have in the Delphi results. Yeah? So therefore, it was then decided that this would be maybe too complex to produce really meaningful results from a system dynamics model.
Okay. There is a question for the simulation modeling. Perhaps this is for Maria again, by Albert.
Mm-hmm. For the macroscopic simulation method, no, the potential long-term residential relocation did not taken into account. Basically, the simulated scenarios were different only in the market penetration rate of connected and autonomous vehicles.
if I can just add to this, I think what I stated in my introduction was that especially such aspects would be good. I mean, to build on top of the simulation results and feed this into a system dynamics model. Yeah, but at least in my understanding, the microscopic simulation method and even the mesoscopic simulation method would be here a bit limited to consider such effects.
Yeah, that's true. And as Maria said, also in the mesoscopic simulation, it was just considered by the reduced VTTS. So that's kind of what you have mentioned with the lower burden by being stuck behind the wheel. So it's not actually related directly to the congestion time, but more sitting behind the wheel of an automated vehicle. That has been considered, but neither have we considered in the mesoscopic simulation the changes in the population. So the agents were doing their same activity plan as it has been done with the different, among all different market penetration rates.
I don't see any other questions, but perhaps anyone from the panel would like to add something before we get into the concluding remarks. I think we have responded to all the questions. I hope that the presentations were interesting and useful for everyone. They will be available at the Levitate website very soon. So you can dig in, and of course you can contact us for any further discussion. And under this, I would like to proceed to the concluding remarks. We do have a couple of minutes more. I was afraid that the system would close at 11:30, but it was not the case. Today's webinar, we have worked on the different impacts in their assessment methodologies for automated urban transport services. Impacts on the environment. We can see that microsimulation results indicated that the introduction of AVs in the urban environment will significantly reduce CO2 emissions, and the introduction of automated urban shuttle services will lead to a similar emissions reduction as the baseline scenario. And the Delphi results indicated that all sub-use cases will increase energy efficiency. Finally, point-to-point automated shuttle services will lead to the largest energy efficiency increase in the long term. In terms of mobility, according to experts, access to travel will be increased by the introduction of the shuttle services. Kilometers traveled and congestion levels depend on the CAV's market penetration rates. And during the transition phase, when conventional and mixed levels of first and second generation CAVs share the urban road congestion levels are going to increase. And anywhere to anywhere shuttle services lead to the largest reduction in travel time. Modal split using public transport will be mostly affected by the introduction of CAVs, and modal split using active travel will be less affected. The vehicle use rate will be reduced after the introduction of the shuttle services compared to the baseline scenario. And vehicle occupancy will be reduced after the introduction of on-demand automated shuttle services. In terms of impacts on society, safety, and economy, we have quantified the road safety increase after the introduction of CAVs and shuttle services. At larger shares of second-generation vehicles of 60 to 100%, the crash rate of urban transport vehicles can reach a reduction of up to 50 and 69%, which is quite significant. And the Delphi results indicated that all automated shuttle services will improve accessibility in transport. And the point-to-point shuttle services is expected to deliver extra benefits for the city in terms of vehicle operating costs, less parking, and better public health. Finally, to conclude, it was quite important that we quantified impacts. The results confirm the results of other studies showing positive impacts on environment, economy, society, and safety are to be expected when larger shares of first and second generation cooperative, connected, and automated vehicles are introduced in the urban traffic system. The benefits in terms of higher energy efficiency, better access to travel, improvement of public health, and lower vehicle operating costs have been estimated from the introduction of point-to-point automated shuttle services, and to a lesser degree from on-demand services. And all this is quantified. And all these results are introduced already in the LEVITATE policy support tool, which is going to be public very soon, following of course, the necessary transferability studies, in order to give access to the impact assessment tool to all city managers and policy makers starting in a couple of months, in few weeks, where all this quantitative impact assessment can be used in this new sophisticated tool. And with this, I would like to thank everybody for the participation. Keep checking the LEVITATE project website with this presentation and all the project results, which are more and more in the coming weeks. And very soon, with the release of the LEVITATE policy support tool, that will be very useful for all users. And with this, I thank all the panelists, I thank all the participants, and hope for a safer and sustainable future with automation very soon. Thank you very much.